Hello everyone, today we will discuss about the generalized coordinates. Before starting our discussion to generalized coordinates, first we will define the Cartesian coordinates, polar coordinates, cylindrical coordinates, spherical coordinates. Then we will define the generalized coordinates. Now you know that in our earlier discussion that suppose a particle is in two-dimensional space and it is moving freely. If we have to specify its position in this two-dimensional space, then you know that you will require two position coordinates to specify its position. Those will be x and y. Or you can say that if the particle is moving freely in this two-dimensional space, then it will have 2 degrees of freedom. Right? Now, if I draw a line from O to P, and let us say this distance is r, and if this distance r is making an angle of theta with the x-axis in anti-clockwise direction, then we can specify the position of this particle in two-dimensional space by the polar coordinates, and the polar coordinates will be r theta. And you also know that there is a relation between the Cartesian coordinates and the polar coordinates, and that is like x equal to r cos theta and y equal to r sin theta. Or you can find a relation also, x square plus y square equal to r square, or tan theta is equal to y above x. So r and theta are the polar coordinates to specify the position of this free particle in two-dimensional space. Similarly, we can define the cylindrical coordinates. Suppose a particle is moving freely in three-dimensional space, and let us say it is x-axis, it is y-axis, and it is z-axis. It is the origin of three-dimensional space. You know that what are the cylindrical coordinates. We define the cylindrical coordinates like rho, theta and z. Suppose what is your rho? Rho is a distance in xy plane. We have earlier defined it, and let us say it is rho, and there is a point P. It will have the Cartesian coordinates x, y, z, and cylindrical coordinates will be rho, theta and z. Right? Here you also know that the rho distance is making an angle theta with the x-axis. Here theta is the angle also rotated about the z-axis, and let us say this point is M. Here MP is equal to Z, and let us say OP is equal to R. So here you can have the relation between the Cartesian coordinates and the cylindrical coordinates. That will be like x equal to rho cos theta and y equal to rho sin theta and z equal to z. So these are the cylindrical coordinates, rho, theta and z. The other coordinates are the spherical coordinates. The spherical coordinates generally we define by r, theta and phi. You know that what are the spherical polar coordinates, and there is a relation between the Cartesian coordinates and the spherical polar coordinates, and that is x is equal to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to r cos theta. And we can make a diagram for these. Let us say this is x-axis, this is y-axis, and this is z-axis. E is a point, its Cartesian coordinates are x, y, z in three-dimensional space. The polar coordinates will be, the spherical polar coordinates will be r, theta and phi. Here OP is equal to r, and it is making an angle of theta with the z-axis. And suppose this distance is it is r sin theta, and this is making an angle of phi with the x-axis. So it will have a component along the x-axis that will be equal to x. X will be here r sin theta cos phi. Similarly, here y will be equal to r sin theta sin phi, and z is equal to r cos theta. This is your z. You can also see here that this line is parallel to the z-axis. So if this angle is theta, then this angle will also be theta. So here if this distance is r, then you see that your z will be equal to r cos theta, right? So you can find the a relation between the Cartesian coordinates and the spherical polar coordinates. Now for generalized coordinates, we will take some examples and then we'll define the generalized coordinates. Suppose a free particle is moving in three-dimensional space, then you know that if you have to specify its position in this three-dimensional space, then you know that it will require three Cartesian coordinates, and those will be x, y, z. Or you can say that this particle will have 3 degrees of freedom, right? Now if I say that there are two particles which are freely moving in three-dimensional space, suppose it is particle P1 and it is particle P2. It has the coordinates, say Cartesian coordinates x1, y1, z1, and it has the Cartesian coordinates x2, y2 and z2. Now here these two free particles, when are moving in this three-dimensional space, then this system will require 6 Cartesian coordinates, or we can say that there will be 6 degrees of freedom. Right? Now I consider, now let us say there are three particles. This is x-axis, this is y-axis, this is z-axis. Say this is P1 particle, this is P2, and this is P3 particle. These three particles have the Cartesian coordinates. Say P1 has x1, y1, z1, P2 has x2, y2, z2, and P3 has x3, y3, and z3 Cartesian coordinates. So here, if you have to define this dynamical system which is moving freely in this three-dimensional space, then you know that there will be the requirement of the 9 Cartesian coordinates, or here you will have 9 degrees of freedom for this dynamical system. Now you see that here, as the number of the particles are increasing, the number of the Cartesian coordinates requirement is also increasing to specify the position of the dynamical system. Now suppose there are 4 particles which are freely moving in the three-dimensional space, x, y, and z. Say this is P1 particle, this is P2 particle, this is P3 particle, and this is P4 particle. These are non-collinear particles. Suppose P1 has the Cartesian coordinates x1, y1, z1, P2 has x2, y2, z2 Cartesian coordinates, P3 has x3, y3, and z3 Cartesian coordinates, P4 has x4, y4, z4 Cartesian coordinates. Right? So now there will be for this dynamical system, if you have to specify its position, then you will require 12 Cartesian coordinates, or there will be 12 degree of freedom of this system. Now you see that as the number of the particles is increasing, the requirement of the number of the Cartesian coordinates is increasing, or degree of freedom is also increasing. Suppose the system has n particles, and these n particles are freely moving. There is no constraint in three-dimensional space. Then you know that there will be the requirement of the 3n Cartesian coordinates to specify its position. Right? Now you see here that as the population of the particles is increasing in the three-dimensional space, then it is necessary that there will be some constraints, or there will be some restrictions. So suppose for such type of system in which there are n particles, and there are the m number of restrictions, then you know that the number of the coordinates, now the number of the independent coordinates or degree of freedom will be now reduced, because there are now some restrictions. Okay, so suppose here now the number of the free coordinates or number of the independent coordinates, say small n, then it will be equal to 3n minus n. So n represents the number of the generalized coordinates or free coordinates to specify the position of the dynamical system, right? So these are called as the generalized coordinates. Suppose the position coordinates of the ith particle, if there are n generalized coordinates, then we can write it xi is equal to xi q1 q2 q3 qk up to qn. If it is a constant which is time dependent, then we can write it in terms of time also. It will be a rheonomic constant. Similarly, yi will be equal to yi q1 q2 q3 qk qn t, and zi will be equal to zi q1 q2 q3 qk qn t. For general, we can write it as ri is equal to ri q1 q2 qk qn t. Here q1 q2 qk qn, these are n independent coordinates and are called as the generalized coordinates. Now how we can understand it? Let us take an example here. Suppose a particle is restricted to move on the surface of a sphere, right? Let us say it is x-axis, it is y-axis, and it is z-axis. This is the center of the sphere, and a particle is moving on the surface of the sphere. Let us say the radius of the sphere is capital R. Now you know that there will be a restriction for the particle which is moving on the surface of the sphere, and that is x square plus y square plus z square is equal to r square. Here this particle in terms of the Cartesian coordinates will have three coordinates x, y and z, but in terms of the spherical polar coordinate r, theta and phi. Here you see that one coordinate r is here constant. It is not going to be changed because the particle is always moving on the surface of the sphere. So capital R is always constant. What can be changed here? Here theta and phi can change. So theta and phi here will be the generalized coordinates, right? So if we have to write these generalized coordinates in terms of the Cartesian coordinates, then we can write these like x is equal to x theta phi, or if theta, let us say it is say q1 and phi is say q2, so we can write it as x is equal to x q1 q2. Similarly, y can be written as y theta phi, and it will be written as y q1 q2. Similarly, z is equal to z theta phi, and it can be written as z q1 q2. Similarly, we have written in our earlier slide that xi is equal to xi q1 q2 qk qn t. Right, here t is not involved because whenever we want to find the position of the particle on the surface of the sphere, its distance from the origin will always be constant. So here t, we can neglect t. Time is not involved. Then the constant, the holonomic constant, is also called as the cylindrical constant. We will define just as velocity corresponding to a coordinate rj is defined as rj dot, or it is equal to drj or dt. Similarly, we can define the generalized velocity, and the generalized velocity will be defined as, it will be qk dot is equal to d over dt qk. Now if you have a function like suppose g is equal to g, it is a set of the generalized coordinates and time, then the time derivative of this g will be like dg over dt can be written as sigma k del g over del qk into dqk over dt plus del g over del t, or it can be written as dg over dt is equal to sigma k del g over del qk qk dot plus del g over del t. It is for a holonomic constant. Right, if it is a cylindrical constant, then we can write dg over dt as equal to sigma k del g over del qk qk dot. The usefulness of the generalized coordinates is that the usefulness of the generalized coordinates is that number one, the constraint forces already removed from the dynamical system, and number two, these are independent coordinates. Does not depend upon each other. Means these can have the dimensions of like length square, or volume, or velocity, or momentum, and so on, right? Further, for holonomic constants, you have to remember this. This is a very important relation, and it is called as the dot cancellation law. Dot cancellation law, and it is written as like del Ri or del Qk can be written as del Ri dot over del Qk dot. Thank you.